Hello everyone. Hello everyone. Today we have a pleasure of having Hitansh Shah from the University of Houston giving a talk on QCD critical point, locating it from lattice QCD. And Hitansh is a fourth-year graduate student at the University of Houston working with Volodymyr, and he is visiting us for this and the following week. And so we have the pleasure of having him talk about his recent work. So please, Hitansh.
Yeah. So, hey everyone, I'm Hitansh, graduate student at University of Houston. First of all, I would like to thank Volodymyr and Vovchenko and the organizers of this seminar for giving me this opportunity to present here. So, my topic for today would be locating the QCD critical point from first principles through contours of constant entropy density. This is the work we did last year, and it is based on the work on the Sartre number given over here.
Do you have your microphone on?
No.
Okay, sounds like it. Okay, go ahead.
Oh, there's also the audio. Even the microphone's on, if your speaker's on.
Sorry?
The speaker is also off, right?
You have to disconnect from audio from the laptop. You don't have to. You should.
Okay, go ahead.
Okay.
Just sound as if there were some.
But I mean, not just the speaker, but also not just the mic, but also the speaker.
Yeah, you just switch off the sound.
Yeah,
Is
So
that
sure.
just disconnect the audio from the speaker.
So here is the phase diagram of strongly interacting matter, where on the vertical axis we have temperature and on the x-axis we have the baryon chemical potential. Now we know that at lower temperature and baryon chemical potential, the phase of QCD matter is a gas of hadrons and resonances. And when we increase either the temperature or the chemical potential over here, this hadrons deconfine to a new state of matter, which is the quark-gluon plasma, or the QGP, which is the most perfect fluid found in nature. Now, at zero chemical potential on this vertical axis, we know that from first principles lattice QCD simulations, the transition from hadrons to deconfined quark-gluon plasma is an analytic crossover. Now, due to the fermion sign problem, one is not able to do these lattice simulations at finite chemical potential, but many models predict that at finite chemical potential, this crossover transits to a line of a first order phase transition that ends at the critical endpoint. This critical endpoint is what many people are trying to find, and this is what we are trying to find using contours of constant entropy density from first principles lattice QCD calculations. Now, one can also look for this critical point through heavy ion collisions, where we collide heavy ions such as lead, and gold, and as you decrease the collision energy, one scans higher and higher values of chemical potential. So, for first principles calculations from lattice QCD at zero chemical potential, how we find the equation of state. So for this, we discretize the space-time into a four-dimensional lattice where the quark fields are on the lattice sides and the gluonic fields are the links between these quark fields. And we try to discretize this and solve the QCD partition function numerically as given over here, where the partition function is integrated over the anti-quark fields, the gluonic fields, and here is the action of QCD. Now, when you integrate over quark fields, we observe the partition function looking like this, which where we apply on this term Monte Carlo sampling to integrate this partition function. Now, at zero chemical potential, this term, it is real. So one can use this term as a statistical weight and apply our Monte Carlo sampling. But when you go to finite chemical potential, this term becomes complex. And because of this, one is not able to perform the Monte Carlo sampling and cannot solve the QCD partition function. So at zero chemical potential, one can solve this, and we observe the equation of state obtained over here, where we have the trace anomaly, the pressure, and the entropy as a function of temperature at zero chemical potential from two different lattice groups, the hot QCD and the Wuppertal Budapest collaboration, and their thermodynamics is within error bar of each other. So lattice QCD can only be applicable at zero chemical potential, and one can also not perform simulations lower than 110 MeV because they become computationally heavy. But one can still perform the lattice QCD simulations at imaginary chemical potential, because in that case, again, this term would become. So there are many applications to obtain the QCD critical point using this lattice QCD data. One such application. Yes.
Random question. So if you have a quantum computer, you don't have a sample.
Yes, maybe. The conjecture that when you have a quantum computer, that we can not have this sign. Yes, I think it is still computationally heavy to do this there, and people I think are trying to perform this such kind of simulations, or not a similar kind, but at least try to solve QCD. In that case, I'm not sure how much ahead they have been. Yes, so one method to obtain for the conjectured critical point at real chemical potential is through Yang-Liat singularities. So because the QCD simulations are possible at imaginary chemical potential, and critical point being a singularity in the real axis, which turns to these Yang-Liat singularities in the imaginary plane, one can look for these Yang-Liat singularities in the complex plane through lattice QCD simulations, and through Parefit they try to approach the real axis and see if they are able to find this critical point. So this was done again by both the hot QCD collaboration and the Wuppertal Budapest collaboration, and what they find is the extrapolated CP from these Yang-Liat singularities to be at a temperature of 90 to 110 MeV and chemical potential of 400 to 600 MeV.
So is that the conclusion from the right plot as well?
No. So the thing is, this is with statistical error, but systematics are not applied. So what they also find is that from the right plot that the error bar could go higher and higher, and not just this. This is mostly coming from this QCD correlation.
They only rule out the Wuppertal guys, right? I mean, they can make an exclusion plot, but they cannot tell where it is. They can only tell you where it shouldn't be, right?
Yes, actually they also use an exclusion, which I will show afterwards using our method as well. And
Yes, actually, I think they did make some estimate of exclusion based on this particular thing, the Yang zeros, and if I remember right, it was something like below 80 MeV or something like this. Or rather above 80 was excluded, something in those range. But I think they were very uncertain about this because they can get anything depending on changing the scaling, which should converge to the same thing in theory. But yeah, I guess that's an aside here.
Do all the different temperature determinations have the same ion mass calculations?
I think yes, they fit to the real pattern, physical pattern.
And on the bottom on the left, is that black line supposed to be like the singularity of the Yang-Liat?
Yes, this is them trying to perform the scaling from, this is all in the imaginary axis, and then they are trying to go to real. So they are just doing one parameterization of all the imaginary singularities they find and try to go to real axis. That's what this black line is.
This number is the static medium without dynamic effect.
Sorry?
This number is calculated from the static.
From statistical, not static. So another way to look for critical points in the literature is through the Dyson-Schwinger equations, where they look at mesonic backcoupling and see how much the backcoupling affects the critical point, and they find a critical point regime of 600 in μb and temperature around 120 MeV. Another way is to use the functional renormalization group, which again gives a critical point in a similar ballpark of 600 to 650 MeV in μb and temperature around 100 MeV. One more method is using the black hole engineering. So what they do is use the gauge gravity correspondence to and map a 5-dimensional black hole theory to a 4-dimensional quantum field theory, where in this case it is mimicking QCD at zero chemical potential, and try to then go to finite chemical potential from this gauge gravity correspondence, and they find a phase transition between two strongly coupled liquid around 518 μb and 105 in temperature.
Don't step on your shoelaces.
Yeah.
So I remember that I think someone told me that in general you cannot use this black hole stuff on all phase diagram. So maybe you can remind
yes.
me why we think that in region of critical point it works.
So this correspondence should work because this correspondence is for strongly coupled system, and around the critical point the system is or near the phase transition the system is strongly coupled. And
remind me why we know it precisely.
Because
And again, what is strong is like some kind of effective.
You can say the running coupling constant is still strong in the
Yeah, but
QGP.
I mean, there are not such kind of boundary, or there is some kind of number, some kind of analytical result after which ADS CFT fails.
I think ADS CFT where it fails, I'm not sure if there is a number, but it works for a strongly coupled system, which QGP should be near the phase.
Yeah, I mean, maybe you can elaborate where I can read what is strongly, what is not strong.
I think
This
it's
is a
over
question.
S is usually shear viscosity.
Yeah, I know, but
Yeah, so that's where that 1/4 is
I
projected.
see.
Lower bound is what is ADS CFT utilizes.
But they effectively see that it fails, or they have some kind of analytical expectation that
It
it
is
fails.
1/4 as far as I
Yes,
understand.
it is.
Okay, I see.
Strictly, yeah.
It's
No,
strict.
it's
Yeah.
not exactly that, especially in some corners of phase diagram.
Yes, actually, for their equation of state, I think at all points they get 1/4.
Okay. Thank you.
Yes, and so all of these approaches are tuned to lattice QCD at zero chemical potential, and there are also other estimates such as finite size scaling, which uses the experimental data to locate the critical point.
So should I,
Yes.
how to transfer the Christian energy for this temperature and chemical potential?
It should be around 4 to 7. I actually have a plot for this chemical potential afterwards comparing to collision energy, so I can show you that. But around 4 to 7. Yes. So another approach where we can use lattice QCD is through.
That's true. I guess. Yeah. Take a slide. You might want to click on your slides too. Okay.
Okay. So what one can also do is use expansions on lattice QCD data and go to finite density. And the most intuitive expansion that one can use is the Taylor expansion, where which is shown over here, where we are expanding.
Laser.
Laser.
The screen is not reflective, so the
I
laser
see.
doesn't.
So here we are expanding pressure in terms of temperature and chemical potential, as which is equal to pressure at zero chemical potential plus this higher order terms of mu b over t, where the coefficients are the susceptibilities calculated at zero chemical potential. So the coefficients are given over here, which are corresponding to second order coefficient over here, fourth order over here, and so on and so forth. So one can do Taylor expansion of lattice QCD at from zero chemical potential, and what one finds is that as you go, so first of all, as you go to higher and higher derivatives, the error bar on the susceptibilities increases. And so the limitation to this is that it is an expansion in constant temperature. So it does not have the curvature of transition line. Also, it is computationally difficult to get higher and higher susceptibilities, and also at the critical point, Taylor expansion should break down. But this expansion can give us an equation of state which is valid up to mu b over t value being less than equal to 2.5. And yeah, this expansion was performed both by the hot QCD and the Wuppertal Budapest collaboration here. So another smart way I think to expand is to resum the Taylor expansion based on this ansatz over here. This is the T prime expansion, and the basis of it is that the quantity when they looked at it from the Wuppertal Budapest collaboration, T chi1 over mu b as a function of temperature for different values of mu b over T in the imaginary plane, and it looks something like this. So what they found is that when you scaled the temperature over here, all of these quantities look like chi2. So the answer is that T chi1 over mu b at finite chemical potential is equal to chi2 at zero chemical potential, but the temperature is now shifted. And this shift in temperature is given over here, where the expansion for the shifted, the expansion coefficient for the shifted temperature is kappa 2, which depends on the fourth order susceptibility and the second order susceptibility, and it is given over here. They also calculate kappa 4, which is the next order term, and it is almost very close to 0 given over here. So using this expansion, they were able to get an equation of state up to mu b over t less than equal to 3.5. But this expansion again did not give any description of the critical point up to mu b over t 3.5 and got a crossover till then. A recent update on this expansion was that this was performed by the Houston group in collaboration with the Wuppertal Budapest group, and they obtained a 4D equation of state in the plane of temperature mu b, mu q, mu s using this T prime expansions here. And they were able to obtain a higher coverage in the four-dimensional equation of state compared to the Taylor expansion. And this work is over in this paper over here. So what I will
sorry, can I ask a question?
Yeah.
So in the upper right plot, is this scaling purely empirical? I mean,
yeah.
Right. Is it any underlying reasons, or is it purely by experience?
No, I think one is one can just apply L'Hopital on the left hand side over here and see that it corresponds to chi2, and I think that is the main basis behind it, that okay, this scaling, this should be the case as you go to higher and higher chemical potential, but your coefficient of expansion should also change. So what they thought before is that this this scaling would have a constant kappa value, but then they find that kappa is actually dependent on temperature, but it is just something that they find, and it kind of makes sense mathematically because it is just L'Hopital on the left hand side.
Okay, thanks.
So if I get this right, so that it scales at fixed temperature makes sense because that's how you match the expansions, right? But the fact that kappa is almost independent of temperature is more of an empirical observation.
Yeah, that is an empirical.
That kappa 2 is almost constant is empirical, but that it falls on the same line is because you match the expansion, right?
Yeah, exactly.
Okay.
So the previous two expansions that I showed were not able to give a description of critical point, but what I will be showing you now is that when you have an expansion that follows contours of constant entropy density, you might be able to give a description of critical point. And for this, first we try to understand how contours of how entropy density behaves as a function of temperature, as shown over here in the left plot for curves of constant chemical potential. So at lower chemical potential, mu1, where we have a crossover, our entropy density monotonically increases as a function of temperature. Now, if you have a first order phase transition in the system, then as you increase the chemical potential, you observe that at the critical point you have a diverging slope for entropy as a function of temperature. And this diverging slope is given over here by this blue line, and the star depicts the critical point corresponding to the critical chemical potential mu Bc. Now, when you go to chemical potentials which is higher than this critical chemical potential, you observe this S shape corresponding to coexistence region. That is, both of your phases, hadrons and QGP, are coexisting in this region, and we have the spinodals over here. Now, unless a Maxwell's construction is employed, then at a particular value of chemical potential and temperature, we should have three different values of entropy density. Now, when you map this in a T mu B plane and look at contours of constant entropy density inside, we observe that at lower chemical potentials, these contours, they do not intersect each other and are almost parallel to each other. But when you go to higher values, where in the regime of a first order phase transition, you observe that these contours cross each other because you have three different values of entropy at the same value of chemical potential and temperature. So what do we learn? That if the contours of constant entropy density do not cross, it suggests an analytic crossover. But if the contours do cross, it suggests a first order phase transition in the system. So one can follow these contours of constant entropy density if we have the entire equation of state of the system, but that is not the case in QCD. We only have the equation of state at zero chemical potential. So what do? Is we do a power series expansion for these entropy density contours, and this expansion is an expansion of temperature at constant constant entropy as a function of chemical potential and T0, where T0 is the temperature at zero chemical potential from which the contour of entropy density is starting from. So our temperature, so it is a function of T0 plus higher order terms of chemical potential times the coefficient of expansion alpha. And this coefficient of expansion alpha, they are calculated at constant entropy density but zero chemical potential. And in our work, we truncate the expansion to second order in mu B, which gives us the expansion equation over here, where alpha 2 is the coefficient of expansion at second order, calculated at constant entropy density and zero chemical potential. And it turns out that the alpha 2, it is dependent on chi2, its temperature derivative, and the temperature derivative of entropy density.
Why you stop at second order?
Okay, this is something I'll show afterwards as well, but the reason is that we want to do a rigorous error analysis of the critical point location that we obtain, and when we go to higher order, we need not just these terms but also chi4 and its temperature derivative and double derivatives of chi2. And as you have more and more derivatives, it's difficult to perform an error analysis.
So this form of expansion in this case is just some kind of your assumption. I mean the first row. Because I compare it to the T prime expansion. In T prime expansion, you use the ansatz. So what is the ansatz here?
The ansatz is just that your expansion should have constant entropy density. So when it's following the contour. So you are basically following a curvature which has constant entropy density.
I guess, can I say that you just manifest this expansion in the simplest form which suits you, and then you want to follow the entropy density?
Yes.
So then itself it's already an ansatz.
Yes.
You just count the alpha so that it would fit your needs in this expansion.
So why is it ansatz? It's just an expansion. leading order expansion. So
Well-
it's unique.
Yeah, the alphas are unique. You calculate based on, okay, you are calculating that total and change in entropy density goes to 0, and from there you start developing this expansion and the alphas.
It's a kind of Taylor expansion along the line.
Exactly. Yes, it is a Taylor expansion.
Okay. Then I understood. Thank you.
So because we are going to deal with temperature derivatives of the lattice QCD data, we parameterize the lattice QCD entropy density and chi2, and the parameterization is given over here, where the red letters are the different parameters. So to calculate the parameters based on the lattice data, we perform chi-square minimization, and we obtain the mean value of the parameters, which goes right through the mean value of the lattice data. So the solid black line is the mean value of the parameters, and the orange bars are the lattice QCD error bars.
Why is T0 a parameter? I thought this is the temperature.
No, it's okay. It's not the
It's
T0
input.
temperature.
It's not a parameter.
Yeah,
It's what you put
it's
in.
just a not so great label.
Yeah.
It's here it becomes T actually, the T0.
Oh, wait.
No, T0 is a parameter.
T0 is a parameter.
It's not the T0 on the previous
No,
slide.
it's not the yeah.
Oh, okay.
Yeah,
Alright.
it's a completely different. You can
Yeah,
just call it
parameter.
X. Yeah.
Inflection point. So the Hitansh is the inflection point.
Yeah, but on the previous slide, you had the T0 for the temperature, 0 chemical potential.
Yeah,
Yeah, it's not the
Yeah,
same. I should change this to some other.
Different object, yes.
Yeah.
Yes.
Okay, so we perform the chi-square minimization to get the parameters values, and also apply Monte Carlo sampling to get the lattice QCD error bars, which is shown by this gray lines over here. So now that we have the thermodynamics at 0 chemical potential required to obtain alpha 2, which is the expansion parameter at second order, we observe how alpha 2 looks as a function of temperature, and we observe a non-monotonic behavior in alpha 2 over here. So how do we obtain the critical point location using this expansion? So what we do is, so for this we rely on the temperature derivatives of alpha 2. So the first and second derivative of alpha 2, and how we obtain the critical point is,
I thought it's a speck on the screen, so it's alpha 2 prime and alpha 2 double
yes,
prime.
alpha 2 prime and alpha 2 double prime.
Okay, good.
So we find the critical point location based on the fact that critical point is an inflection point. That means that this quantity del square T over del S square at the critical chemical potential should be equal to 0. So when you apply this rule, this identity in our expansion, we obtain this identity over here, where T0C is the temperature at 0 chemical potential from which the contour of critical entropy density starts from. And what we obtain is that wherever alpha 2 double prime goes to 0, so wherever this curve goes to 0, we obtain, that's where we obtain the critical T0C value.
So you have two critical T0s now?
Yes.
Okay.
So I will get there.
Very
to
good.
Why the
It's
second
always
one
good to have a choice.
I will show where the second one is coming from,
Okay.
or we think where the second one is coming from. So
But hold on, just before you go. So you don't need to go into the coexistence region. You can do this at the critical point.
exactly.
So even if you have non-mean field, you don't have to worry about this at the critical point. Life is good.
Exactly.
Okay,
yes.
good. Thank you.
So to obtain the critical chemical potential, we use the fact that del S over del T diverges in the first order phase transition, and at the critical point, which implies that del T over del S goes to 0. And when you apply this identity on our expansion equation, we obtain the critical chemical potential given over here, which depends on this alpha 2 prime and the T0C obtained before. So
Ts by dt diverges at where exactly at the first order field.
And the
Spinodal bound.
spinodal.
So there you need to go inside the coexistence.
Yes, but you also have a diverging slope at the critical point, right? Which would mean that this
The,
would go.
the SDP, yeah, that's my question, right? I mean, so is that true already at the that's true at the critical point already, right?
Yes.
Okay, good.
So using the critical chemical potential and T0C, we can obtain the temperature at finite chemical potential where the critical point is. So now that we have alpha 2, we can look at the finite temperature and chemical potential and expand, and what we obtain is the normalized entropy density shown on the left as a function of temperature at constant values of mu b over t. And what we find is that it agrees with the already available lattice QCD data up to mu b over t less than 3.5, which was obtained from the T prime expansion scheme. So we already agree with the previous expansion scheme, and we try to push this expansion to higher chemical potential values. And this could be seen on the right plot over here, where again I have normalized entropy density against temperature as a function at constant value of chemical potential. And what we find is that at lower chemical potential values, we have a crossover around 450 MeV, and a critical point location for the mean value of the parameterization was obtained at mu b being 602 MeV. And for chemical potential higher than this critical chemical potential, we obtained this S shape over here, suggesting a first order phase transition.
You predicted the critical point is around temperature around 150.
100, yes.
So can you give the uncertainty for this critical
Yes, the uncertainty is exactly in the next slide. So here is the uncertainty for the critical point location found at order of mu b square, which is 602 plus or minus 62 in chemical potential, and TC was 114 plus or minus 7, and this corresponds to the red ellipse over here, which is the 68% confidence interval, and the black dot over here is the mean value of the critical point that was obtained. The solid black line is the line of first order phase transition, and the dashed lines are the spinodals that we obtained in the T mu b plane. So we also compare it with the lattice QCD crossover shown in green over here, which is obtained from the curvature of transition line from lattice QCD, which is up to 400 MeV in mu b, and we find our critical chemical potential to be higher than this value. The orange curve over here shows the chemical freeze out bound from experiments, which is the bound which is a point in experiments where there are no more inelastic collisions in the system, and the system is hadronic. So this gives us a lower bound in temperature on what our critical point value should be, and our critical point is higher than this lower bound. It is important to note that the chemical freeze out bound shown over here is for mu q equals mu s is equal to 0, and not for the strangeness neutral conditions from heavy ions, and it was obtained from this paper over here.
So why is your uncertainty on the chemical potentials like almost a factor of 2 larger than for the critical point? I mean, they have 10% versus 6% or something like that.
So this one comes from the uncertainty of lattice for alpha 2, right? While I think the temperature one.
One is the first derivative and the other is the second derivative. Is that where it comes from?
Yes, that could be true, because the second derivative has uncertainty in temperature, which we obtain for critical T0C, which is pretty small, while in the other one you also have the uncertainty coming from the first derivative.
Well, I guess also the curvature of the line. If you were at if critical point was at small mu b, there would be very small uncertainty in t, but larger uncertainty in mu b, right? So I guess it's the
Oh, maybe that's just what it is. Yeah, okay. Maybe it's so simple, yes. Okay.
So you parameterize this lattice data function. How strongly is the prediction depend on the parameterization in the your T temperature region?
You mean the correlation?
Yeah, the entropy.
Page 10.
I think entropy as function of temperature is lattice data. You parameterize use some function and use that to derive all those predictions.
Yes.
How sensitive is the prediction depending on the function?
Yeah, it is actually quite sensitive because you not only need the entropy, but what you also need is entropy derivative with respect to temperature. So this makes it more sensitive to changes in entropy as a function of temperature. So if the entropies change a little bit, you will see a difference in
Shouldn't that be part of your uncertainty?
Yeah, it is part. I think the question was how sensitive it is to a choice of particular parameterization,
That's
right?
right.
And this you have,
I
right?
see. Yeah. This I have actually. So, sorry, I thought something else that was the question. But okay, so what we also did is instead of using parameterization, we spline fit the lattice QCD entropy and chi2b. And what we obtain is the critical point location given over here, which corresponds to this blue ellipse over here. So they still overlap the critical point region within one sigma confidence interval. And yes, so from this, what we found is that the collision energy from 4 to 6 GeV seems to be close to the vicinity of the critical point.
Can you estimate the often if you include higher order mu b? Just adding 10% or 20% or you overall shift to the mean value?
Sorry, if we go to higher order in expansion.
Yes.
If we can estimate going to higher order in expansion, but then we are also cutting off.
Do some estimation roughly how many percent?
That would still be difficult because in that case the error would increase a lot because of the higher order derivatives. So it could still be pretty cumbersome to obtain a rigorous chemical potential estimate in error because you have chi4 derivatives, chi2 double derivatives, and also to calculate the critical point, you also need the next order coefficients, temperature derivatives, double temperature derivatives. So it could be a bit tricky to actually obtain it. So yeah, I will also get to that later on a different way to look at these contours and how we can get a better uncertainty instead of going to higher order expansion. Yes, so here is the recent critical point development in the literature and compared to our critical point estimate, and we observe that the critical point estimates from the literature such as black hole engineering or FRG, they are all in the same ballpark in chemical potential, although for temperature we might have slight differences with other critical points, but it is important to know that here we are only showing the mean value of the critical point for the other estimates and not their error uncertainties.
So which one of those has lattice information? The black hole engineering.
The black hole engineering does.
Young zeros.
Yeah.
How about FRG and Schwinge? Are they?
I think they are also tuned to lattice.
Are they tuned?
Well, depends who you ask.
Yeah.
So they are benchmarked.
Benchmark. Okay.
Against lattice, but what does it mean?
Okay. All right. So, okay.
Yeah. The only one that is not kind of tuned to lattice is the finite size scaling, which comes from experimental. Okay, so we also use the mean value of parameterization for entropy from the hot QCD collaboration data, and we obtain a critical point location shown over here, which is still inside our 1 sigma confidence interval. And yes, when you look at alpha 2 double prime, which has second zero, and when alpha 2 double prime goes to zero, that's where our critical T0C is. We see that this solution at a higher temperature, around 160, corresponds to a critical point at finite imaginary chemical potential, and what we get is Tc of 194 plus or minus 7, and mu b over T being I times 3.5 plus or minus 0.3. And it appears to be close to the Roberge-Weiss critical endpoint, which is at mu b over T being equal to I times I. So to perform a controlled test on the critical from our expansion, we use the holographic black hole model, and we try to use our expansion in this model. So this model is again obtained from the gauge gravity correspondence, and it gives a good description of lattice QCD data at zero chemical potential, and contains a phase transition between two strongly coupled liquid. And in this model, the contours of entropy density were nearly quadratic, as shown from the solid black lines over here in the T mu square plane. They look almost linear. And when we obtain alpha 2 from the data from the black hole engineering at zero chemical potential, we get the alpha 2 over here, from which we obtain the extrapolated contours shown by the pink lines, which is almost following the true contours of the model, and has the spinodal region almost on top of the spinodals from the model as well. And the true critical point in the model is at temperature 103 and mu b 599, and what we get is a temperature of 104 MeV and 637 for chemical potential. So pretty close in terms of temperature as well as chemical potential. Yes.
So how you can build these contours inside of the mixed space?
So we just extrapolate and see wherever they cross, and we obtain the contours.
Okay, and the model itself is a mean. It's not a mean field.
It's a mean field.
It's a mean field. Then I understand.
What about the first quality? What do you mean? Good description of lattice plus QGP non.
Yes, it means that it contains a phase transition between two strongly coupled systems, which is also in case in the QGP lattice.
But also lattice data.
Yes, also lattice data. So it is fit to entropy and chi2b, and it was able to obtain all the other thermodynamics of lattice QCD data, such as pressure, rotation. So analysis of this expansion's properties and looking at different observables is currently a work in progress as well. So what we also want to check is test this expansion on a model which has 3D in critical exponents. So for this, we use the Lennard-Jones potential over here, which has this short-range repulsion term and the attraction term, and it contains a phase transition from gas to liquid and has a critical point which is in the 3D in universality class, similar to QCD. And because we can change the location of the critical point in this model, we want to see how sensitive this change in critical point location is for our contours, for our entropy contours truncated expansion. And also because our expansion is mean field in nature, we want to see that it is still able to recover the correct value of the critical point, even if the critical point is in a 3D easing universality class. So this is also currently a work in progress, which we will be doing with Vovchenko. Yes. So we are not saying that we obtain the QCD critical point. Of course, what we are saying that it is a proof of principle in the sense that this is an expansion that can describe the critical point by following contours of constant entropy density. However, the accuracy would still depend on how good the truncated expansion is. So in our work, we truncated second order, but how was the fourth order term looking like? So when you go to the next order, this alpha 4, as I mentioned before, has chi 4 prime, chi 2 double prime, and s double prime. So double derivatives of entropy and chi 2 with respect to temperature. And to calculate the critical point for this, we will have to solve a couple set of equation which also has which also has alpha 4 prime and alpha 4 double prime. So to get a rigorous value of the critical point based on the error bar would become more and more difficult because the temperature derivative would lead to larger and larger values of the error bar. So for this, what we suggest is to look in the imaginary chemical potential side. So from the imaginary chemical potential, we can look at the contours of constant entropy density, and we can observe and we can fit that and we can obtain the coefficients from fitting to those contours and then extrapolate to real chemical potential. And this was recently done in the strangeness neutral direction, whereas what we have is mu q mu s is equal to 0. And this was done by the Wuppertal Budapest lattice QCD collaboration. And what they obtained is an exclusion plot of critical point for mu b less than 450 MeV. So what they looked at is not the coefficient itself, but where they find crossings at real and finite chemical potential. And what they observe is they do not see any crossings for chemical potential less than 450. So to summarize, we developed an expansion scheme that follows contours of constant entropy density and can provide a description of a first order phase transition. It agreed with the already available lattice QCD data for mu b over t less than equal to 3.5 and obtained a critical point location for order mu b square for the parameterization for the lattice QCD thermodynamics, and the critical point is given over here. And we find that the collision energy in the range of 4 to 6 GeV in heavy ion collision is predicted to be close to the QCD critical point. And an analysis of this expansion on variety of models and also looking at other observables and how sensitive the critical point is for those other observables is still a work in progress. Thank you.
Thanks, Hitansh. More questions?
So if you want to compare the data in which dynamical effect, can the lattice or your framework can include some dynamical effect, for example, finite size and finite time?
Finite size from this. What we can obtain is equation of state from this. Finite size scaling could be possible based on cumulants or once we obtain chi 2b, but not sure.
The finite time is more stronger than finite size because lifetime is very short.
Yeah, it's static.
Yeah, it's static.
But I wonder that maybe if you do expansion using finite volume data, in principle, it could be a finite volume estimate.
Or maybe you can connect some connecting model for the hydro.
Finite volume, there is strictly speaking no phase transition, right? Which is another caveat. I think Levi has a question.
Yeah, can I ask question? Slide 12, I believe. On that slide, I saw two plots. They have the same labels, but they look very different. Is it something wrong with the labels, or?
No, it is because on the left plot, for each value of mu b over t, it is being multiplied by 1, 1.3, 1.6, 1.9, and so on. So that the error bar looks different. It's more for aesthetics sake. But yeah, if you divide this with the corresponding multipliers, you should get a similar vertical axis.
But why the curve looks so different?
I never get the S shape on the left, this right?
Oh, because on the left we only go to mu b over t being 3.5. We do not go into the region of first order phase transition there.
Well, like, I guess it's also
I
mu
see.
b over t versus mu b constant, right? Lines, right? One is mu b over t, the other is mu
Oh,
The
oh,
left plot is
that's
mu
it.
b over t and right is constant mu b.
I
So
see.
the right side is based on extrapolation.
The right side is going further
Further
from mu
away
b
from
equals
the
0.
first
Yeah.
one.
For period.
Yeah. So if I get this right, the moment I know the curvature of the lines of constant entropy at mu equals 0, I can do this. That's what you do, isn't it? Can you get your alpha equation? I mean, this alpha 2 is just the curvature of the alpha 2 definition is the curvature of the lines of constant entropy at u equals 0.
That's correct.
So if I go now and look at any garden variety model which doesn't have a phase transition, it does that. I mean, once I have these different curvature, if it's just a parabola, eventually they have to cross, right? I mean, even everybody understands, right? But they don't necessarily have to cross in one point, of course, right? Well, how is that?
So if you have
if I have
this
one curve
behavior in
if
alpha,
the higher curve has a stronger curvature than the lower curve, they cross.
then they will cross.
But if I take a third curve in between, they don't necessarily have to
They
cross.
don't necessarily.
So where is it? Where are you sensitive that it has to? They all three have to cross at the same point. In what observer does that show up? Because you never analyze the point where they really cross when you do this.
To obtain the critical point location, we do not use where they cross.
Yes.
For that, we just use this alphas.
Yes.
But okay, one can reproduce the contours from this expansion, and you can see that they cross. And this comes from this S shape over here. It suggests that yes, they should be crossing.
Yeah, I'm just asking myself: is there a simple model which could fake a critical point according to analysis and doesn't have one? Right. That's what I.
Yes. If you have a model where.
What do I have to do, right? I mean, so to make it look like a critical point according to analysis, but it's not there.
If you have a model which, let's say, does not have a curvature from alpha 2 at lower temperatures, but has a curvature from higher temperatures, because then the lower temperatures would have a flat line, and in that case, it is possible that you might get something which has crossings, but the model in itself does not have crossing, because at lower temperatures, alpha 2 is probably not able to reproduce the actual contours, let's say, which probably has curvature, but alpha 2 is they're small enough to not have curvature.
I guess as soon as it's not parabolic, that's our goal.
Oh no, sure.
Yes.
Yeah. Obvious.
Okay, so what's up?
There's a question, I guess slide 17. I was wondering if you could, say, take noise from a lattice calculation and apply it to your model to see how the uncertainty propagates. So your right values, the true to extrapolated. Because they don't have uncertainties, you don't really know how long you do it.
True. I mean,
so you could take like noise from a real calculation that's correlated, propagated into a model, and just use that as a more convincing calibration.
Yeah, this could be done because there is a paper for this model which has a Bayesian inference, which basically takes into account the noise from lattice and develops this different equation of states based on the parameterization that they have, and yeah, then we can look at all of those different parameterizations and obtain something which has noise over here. This could be.
So I'm just curious, exploring the question which Volker mentioned, that if we have field model, right? In this case, in general, there are no any, if you wish, guarantee that your expression will work.
I mean,
because we don't really know how the entropy contrast will behave in arbitrary beyond field model.
Yes, in those cases, maybe we are not able to get the correct behavior of the first order phase transition regime, but because until and unless it's a truncated expansion, we should get a mean field observation. But we think that the critical point location should not change regardless of its mean field or not, because there we don't use this crossings to locate the critical point. What we use is the alphas, and that is coming from zero chemical potential.
My point is that I think we can say quite freely that if we have the mean field approximation of some kind of advanced theory, in this case, we should expect that your result would be valid, although the actual position of the critical point might be not that precisely in that point your result would give you. Because, to my understanding, the equation of state, when we can write it down in the mean field approximation, it might change a lot.
Mm-hmm. Yes, but I'm not sure. Okay, that's why we are doing this, to check that, okay, if we have some different
I'm trying to
universality
understand
class.
your view on this because of this. Because to my understanding, if I would give you the whole 3D-izing equation of state, whatever Leonard-Jones it is, or other potential, it might be the case that you would obtain the critical point, which would be shifted somehow.
Yes,
because
but
it would be mean field critical point, not the actual critical point.
could be, but okay, so when you give me a equation of state which is coming from a different universality class, still we are going to use from that equation of state at zero chemical potential entropy and chi2v to get alpha 2.
Yes.
And not an equation of state from mean field.
So what you're saying that there are no guarantee, but you think it might work?
Yes, we this is something which still needs to be checked, and we are planning to do that. But yes, we think that this should not affect the universality class, should still not affect the location.
Yes, we want to see if we can see the focusing effect, whether it's mean field or not.
Yeah.
But we didn't have the last question. At some point, not anymore.
Okay.
Okay.
In your last slide, you said that you go to the conclusion. Oh, the next one. Oh wait, you say here that the collision energies in this range are those like realistic? I don't have any idea what collision energies are in collisions. Are those like realistic or are those like?
They are very carefully chosen. They are the only range which we don't have good access. We have to wait another 5 years before this experiment in GSI runs.
Yes.
Why?
Thanks. Okay. So, I think we don't have any questions anymore. So let's thank Hitansh again.